All right, let's talk some circular motion stuff. So we did an experiment, or I should say a series of experiments, where you took your magical spinner device. Let me draw a magical spinner. I don't want that color. It's black. There we go. Okay, so we had a ruler and a spring scale. All right, so there's my spring scale. There's my ruler. Spring scale looked like that. It's got a little more of a handle to it. And then it had the spinner device through it with a string attached. And then you had the bob spinning around in a circle. All right. So this was your device. So you're spinning it around. And from that, you collected data. Now, we collected 2 graphs worth of data. First graph we collected data for was the centripetal force, sigma of c, versus speed. All right, so here we kept the radius constant, and we just changed the speed. And what most groups found is that it looked like this. Had an upwards curve to it. So what that means is there's a direct relationship between the centripetal force and speed, or as we'll just use the letter v. But since it's exponential, it would actually be squared, because if you were to linearize that, you'd have to square your speed. So therefore, this is the relationship we got from that graph. Now, we also had a second graph to create, and so this one here was centripetal force versus, and I got a bit of a line here, versus radius. Now this was the tricky one because you had to do your best to try and keep the radius constant. I'm sorry, other one. To keep the speed constant while changing the radius. So you had to do some calculations. It was a little tricky. But when all was said and done, we got a graph that looked like this. So this was an inverse relationship. So what we discovered is the centripetal force is directly proportional to the inverse of radius. Okay, so we already had that said and done. So that means as the centrifugal force goes up, the radius actually went down, and with a small centrifugal force, you'd have a very large radius. So that's what the inverse means. So we had these two, and then I just asked you guys, hey, do we have a relationship between force and mass? And we came to the decision that we already knew this just from our past. We knew that the net force is directly proportional to mass because F equals ma. Bigger the mass, the bigger the resulting force. So those two are also directly related. So we have these 3 relationships here. One from our past, one from the force versus speed graph, one from the force versus radius graph. When we combine all of these things, we get something very interesting. All right, so let's just change my color here. We actually get this equation. Sigma f of c is directly proportional to m v squared over r. Because it's directly proportional to all of these things, just kind of arrange them, numerator, numerator, denominator, you get this. Now, if you were to actually, if your data was really good, you could do this. And if you knew the mass of the stopper and all that stuff, you could do this. If you went back in, you said, well, it's directly proportional, so there must be some sort of variable here, some sort of constant that you multiply it by, kind of like the coefficient of friction, it's just a number. But if you do the math, you end up finding that that number is actually the number 1. So not only is this directly proportional, this is actually equal to. So it's actually an equal sign. So that's the equation that we walk away with when we combine these 3 equations. Now, we also had some other interesting things that we figured out. When we were trying to figure out the speed, we realized that we also had to use this equation of speed or velocity, because it's tangential speed, so it's always in one direction. Anyways, we've realized it was distance over time. And since it was a circle, that distance was the circumference. So that's 2 pi r. And then the time, well, that's the time it takes to make 1 lap around the track. So that's what we call our period. So we also had that from our past. So I'm going to now make a connection between this guy and more stuff from our past. So I'm going to kind of go over here to the right, and I'm going to say, well, we start off with this. Sigma f of c equals m v squared over r. And we have our old friend, never to be forgotten, f equals ma. So sigma f equals ma. Well, we always pick a plane, and since we're always going with the plane in the line of the center of a circle, that's our centripetal. If we now look, there's a lot of similarities. This is the same, that's the same. That means that this is how we define centripetal acceleration. So that's very important. It's so important, I think I'll make it in purple. I'm just feeling colorful today. So centripetal acceleration is now known to us to be v squared over r. So if I know the speed the object is spinning at and I know the radius over which it's spinning, I can calculate its centripetal acceleration. Now if I take this guy here, oh, it's got a v in it, and I jam it over into here, I can get another equation. So I'm just going to do that. All right, so I'm going to put a box around this because it's kind of a thing. I'll put a box around this one because it's kind of a thing. All right, so if I combine these two here, what really is going to happen is I get AC equals V squared. Well, if I square this, I'll get 2 squared times pi squared times r squared over t squared divided by, yeah, that's just the V squared part, divided by r, which looks a little freaky, but don't worry, stuff starts canceling out. It was like when stuff cancels out. So this r will cancel out with that squared, and then what we're really left with is AC equals 4 pi squared r over t squared. So this is useful because you will not always know the speed. You may just know, how many, what the period is. So for example, we did the lab, we didn't actually know the speed. I mean, you could calculate it, you could do that. But if I said, hey, what's the centripetal acceleration? You could say, well, I know the period and I know the radius, so I can directly calculate it. So sometimes it's useful. At any time, if you feel, this is just too overwhelming, you can always make it a 2-step operation where you could say, well, I know the radius and the period, so I can find the speed, and then I can put that speed here and solve for that. You'll get to the exact same place, so no worries. So what that means is that we've got a new, giant quotes on new equation for speed, or velocity. We have a new equation for centripetal acceleration, technically 2 of them. And then this is still good, okay? I mean, this is still a thing. Look, I'm going to write it for like the 4th time on here. Sigma f of c equals MAC. That's still a thing. This is our basic equation that we're going to live and die by. But we can now notice I could replace the a with v squared over r, so I can get this equation. I could also replace AC with 4 pi squared r over t squared and get a much longer equation. All right, so that's basically what we walked away with from the lab. We looked at the shapes, we got the relationships. From the relationships, we got the overall equation, which allows us to kind of make comparisons to equations from our past. And we now know centripetal acceleration is v squared over r. And since we know the linear velocity of a circle is 2 pi r over t, we can replace that to get even more equations. All right, so that's kind of the synopsis of what we did in the lab experiment. So if you have any questions, please let me know. But hopefully that should refresh your noggin. Bye.